Hello and welcome back to chemistry. We're going to continue talking about chapter 11, section 3. We're going to use something that we may finally remember from last chapter, Gibbs free energy, delta G. In chapter 10 we talked about Gibbs free energy with reactions, delta H equals minus T delta S. And we used delta G to figure out if something was spontaneous or not. And we use that for reactions. Well, in this chapter, we're going to continue using Gibbs free energy. We're going to find out that we can figure out melting points and boiling points using this same equation and the same concepts. Entropy is the particle motion. Entropy of particles in a liquid state is more random than in a solid state. As a solid melts, the entropy of its particles will increase. We call that increase the entropy of fusion, delta S of fusion. We also know that particles in a gas are more random than they are in a liquid. We know that as liquid vaporizes, the entropy of its particles increases significantly. They're getting farther apart, they're getting more random. We call that increase, or that change from a liquid to a gas, the entropy of vaporization, delta S with a VAP for vaporization. Normally the entropy of vaporization will be much larger than the entropy of fusion, just because there's so much more of an increase in entropy when it becomes more random as a gas. So just to give you an idea of a few different materials. For nitrogen, delta S of fusion, going from a solid to a liquid form, is 11, while its vaporization is 72. This is joules per mole Kelvin. Water goes from 22 from a solid to a liquid, up to 108 when it goes from a liquid when it vaporizes. So we're seeing significant differences, 5 times, 10 times greater differences. Lead is, say, 10 times greater. Some might only be 3 or 4 times greater when you're looking at the change when it goes into a liquid. Now, because intermolecular forces are not real significant in a gaseous state, most substances will have similar values for the entropy. And if you'll notice, a lot of these are somewhere around 90. A little above, a little below, but somewhere around 90 is what our entropy of vaporization works out to be. Now, Gibbs free energy, we used this equation before, last chapter. Delta G is delta H minus T delta S. And we also learned a negative delta G is spontaneous. So how can we use that in state changes? Well, it applies to to changes of state as well as our reactions. For example, I now have a heat of fusion and an entropy of fusion. If I know that water freezes at 0 degrees, it freezes at 273, will it melt spontaneously at 273? I'm going to use my delta G equation. I would look up these from table 5 in your book. And from table 5 I know that my entropy of fusion is 6.01, and my entropy of fusion, this is my temperature, entropy of fusion is 22 joules per mole. Now notice your differences, kilojoules and joules, they will often give you these. You'll have to change units sometimes. So divide by 1,000 here. And when I do that, I find out that delta G is 0.004 kilojoules or 4 joules. This is a positive number. If it's a positive number, it will not melt spontaneously, which makes sense. This is below the melting point. Not a lot, only 0.15 degrees, but it's still below the melting point, so it will not melt until it gets above the melting point. We'll try this one in class. What's interesting also is I can use delta G to find melting point and boiling point of something. Because I know that delta G, because I know that when something is actually melting and I have solids and liquids both in place, that system is said to be in equilibrium. Equilibrium means some things are turning to liquid, some things are turning to solid at the same rate. When that happens, delta G equals 0. So what I've done here is I've set delta G equal to 0. And I'm going to use this equation. Now I can rearrange this equation to find the melting point. So I'm going to subtract T melting point times delta S from both sides. I'm going to show you algebraically how this works. Okay. So this is going to cancel. So I have delta H of fusion equals T melting point delta S of fusion. Actually, I would add that to both sides. Now, my enthalpy of fusion is equal to temperature times the entropy of fusion. Divide both sides by delta S of fusion. So that will cancel out here. So T melting point equals delta H of fusion divided by delta S of fusion. You need to make sure this is written in your notes. You're going to be using this equation, so pause if you need to. The same thing happens when I talk about boiling point. So here's the boiling point. Delta G is still 0 because it's at the boiling point at 100 degrees for water. I have some molecules vaporizing, some are condensing. It's happening at the same time. So I've set that equal to 0. Again, I can go through algebraically and show you this, but I'm just going to write this down for you now since I just showed you. It's the same algebraic formula. So T boiling point is delta H of vaporization over delta S vaporization. Again, make sure you have this written down. So we can now calculate the melting points and boiling points. If I'm going to go through for mercury, delta G, this is enthalpy of fusion, delta H of fusion, and the molar entropy of fusion. This is delta S of fusion for mercury. And I want to find out what the melting point is. So we know it's going to be delta H of fusion over delta S of fusion. Now notice my little hint here, check your units. Not sure why they like to give you harder things. I have grams there and I have moles here. So I can't just divide these two numbers directly. I have to change one to the same units. So I'm going to take my 11.42 joules per gram, and if I want to turn that into moles, I'm going to multiply it by the molar mass of mercury, which I've looked up on the periodic table is 200.59 grams per mole. Now grams will cancel, and I'll be left with 2,291 joules per mole. So this is going to be delta H. So now I'm going to put these numbers in. So 2,291 joules per mole divided by 9.79 joules per mole K, and I get a temperature of 234 Kelvin. And this is the point at which mercury melts. And I think to myself, does this make sense? Well, I know that room temperature is 25, it's approximately 25 degrees Celsius or 298 K. So mercury melts below room temperature, which makes sense because mercury is a liquid at room temperature. It's one of our few liquids we have naturally. So this does make sense, and this tells us what our melting point should be. What I want you to do now is try to figure out the boiling point. See if you can figure it out on your own, and we'll talk about that in class tomorrow, as well as go through a couple of more examples for you in class tomorrow. So remember, have both those formulas written down. Enthalpy over entropy. Check your units always. Make sure you have joules and joules, moles and moles, or if you had kilojoules, kilojoules, grams, grams. But check your units. It's the only thing that can do tricky for these numbers. Okay? And we will see you in class later.